Okay, this is a really important lecture in the land of influence lines because I think that today you will really like understand how influence lines can change how you perform structural analysis. Because you're going to start thinking of structures a little differently after today, hopefully. That instead of thinking of structures as, you know, here's a structure, here's some loads, analyze it, I'm going to say, here's a structure, here's some loads, what is the worst possible outcome, what is the worst possible permutation of these loads to generate worst case response. And so instead of doing like one structural analysis, we're almost doing all conceivable structural analyses and figuring out the worst case answer. So, but we can also directly apply them to analysis as well, and I'm going to show you that today. Okay. I thought I would just make sure that we're all aware, 5 p.m. next Friday, that's when the project's due. So, right? I'll say this, I am going to give you a homework on matrix analysis that's going to be due after break, but it's not going to be due until Wednesday after break because we'll come back Monday and see if you all have any questions on it and then finish out pre-finals week, or as it was called, dead week, with trusses and maybe a little bit on beams and frames if we have time. So, okay, let's get into it. And I don't really have much to say on the homework. We're just rocking and rolling on that. Okay. Okay, so we are going to still use the Mueller-Breslau principle to draw influence lines. So remember, that's the idea that you remove from the structure the ability to resist a given response of interest. You then move the structure through a unit displacement, and then the resulting deflected shape is the influence line. And I do want you to be at least comfortable with this and with this. So are we at a point now where if I were to somewhat quickly draw an influence line for a reaction or an influence line for a shear in moment, as long as the structure is relatively simple, that everybody would feel comfortable with where it came from? Is everybody okay with that? Okay. All right. Because we are going to draw some influence lines today, but I think what I really want to focus on today is using them. Okay, and that's the theme of today's lecture, is using the influence lines, not just drawing them, but it's like, okay, here's this cool little pretty picture, what do I do with it? Okay, and so I have two applications that I want to discuss with you. And so the first one is what I'm calling direct structural analysis. And so one of the first applications of being able to, with an influence line, is to just use them as a replacement for statics. Okay, so the idea is that, okay, if here I have is a structure and I'm generating an influence line due to a moving unit load, couldn't I generate the response due to any load anywhere? And the answer is yes. Okay, what I'm getting at is, if I can do this problem, why can't I do this one? Okay, with an influence line, and that's what we're going to do today. Okay. In general, the way an influence line works, if we want to use an influence line to do a structural analysis, what we do is we take, so let's say we have a beam that has, 2-point loads and a distributed load. So what we'll do is we'll take, if I want to find, the reaction at A, I will draw the influence line for the reaction at A. And then I will take P1 times whatever the value on the influence line is for the reaction at A. And then I'll take P2 times whatever the value is on the influence line for the reaction at A there. So I will sum up the point loads times their associated values on the influence line. But then for the distributed loads, what I'll do is I'll take the distributed load and multiply it by the associated area under the influence line at that point. Now, some of you might be asking, well, wait a minute, Dr. Mike, what about moments or triangular loads or stuff like that? Teams decided to pop up. What about that? My response to that is, if we wanted to turn this into like a more advanced grad school type course, we could handle that, but there's not really much practical application. You're going to learn on Friday. We're going to talk about AASHTO load models. So we're going to talk about the loads that we design highway bridges for in the United States. And I might even discuss a little bit about rail bridges and other moving loads that we deal with in practical structural analysis. And really the only thing we deal with are point loads and distributed loads when it comes to moving loads. So I don't really feel the need to cover this. I mean, I've been, practicing this stuff for years, and I've never had to use an influence line for a triangular load in my life. So I don't think you will either, okay? But point loads and distributed loads, that's another story, okay? So I want to explain how this works because I want to look at this problem, okay? So let me pull up the notebook here, and let's just sort of digest what I'm asking you here, okay? Wrong example. Okay. So let's just digest what I'm asking you here. So I'm giving you a problem. This is a problem that without influence lines, everybody in this room should be able to do. Let's read what the question's asking. It is asking, determine the support reaction at D due to these loads. I mean, y'all can do that, right? That's not complicated, right? So let's ignore all this influence line hullabaloo and let's just do that, okay? So what I'm going to do, this is how I'm going to do it, is I'm going to say, okay, let's draw ourselves a little, that happened again. Suddenly my pen got a little wider. I don't know why that keeps happening. All right, so let's draw a little line here and so what I'm going to do is static equilibrium. And that's basically just a fancy way of saying, okay, if I gave you this beam and I said determine the reaction at D, what would you do? Ignoring influence lines. How would you, this isn't a trick question. If I asked you to calculate the reaction at D for this beam, what would you do?
Summing moments about A.
Summing moments about A. So I'm just going to sum moments at A to find the reaction at D. So let's do that, okay? So we're going to sum moments at A. And maybe what I'll do is draw myself a little reaction right there just so I have sort of something to look at. Okay, now I've got this 1.3 kips per foot distributed load. So maybe what I'll do is recognize that I can collapse that into a single point load. How much would the point load be? 1.3 kips per foot over a distance of 20 feet. How much would that collapse into? 26 kips. Okay, so this is 26 kips, and its moment arm from A is what? From A is going to be 10 feet. Is that fair? So if I were to sum moments at A, I would have 26 times 10. I'd have 25 times what? 20. I'd have 42 times 30.
25 times 40.
Oh, times 40. Well, yeah, you're right. That's 40. Thank you. This is 60. I don't know what I was thinking. All right. Yeah, 40 and 60. I don't know what I was thinking there. Then dy and 80. My coffee hasn't kicked in, I guess. Okay. So, again, we're treating this basic, all right? So 26 times 10, that's 260. 25 times 40, that's 1,000. And then 42 times 60, I'm going to cheat and say that's 2520. And then, so summing that up, I'm going to get 3780 foot kips is dy times 80 feet. And so I'm going to get dy is, what was that, 47.25? I mean, is that fair? I mean, I did that fast, but I mean, I figured at this point we're good with stuff like this, right? Okay. Any questions? Now, I propose that we can solve this using influence lines. So let me show you how this works. Okay, so we're going to use influence lines. So how do we do that? Okay. What are we trying to compute? Like, what was the goal here? Like dy, right? So can somebody tell me, what does the influence line for dy look like?
Move dy up 1, and then it's just a straight line down to ay at 0.
Like that, right? Boom. Exactly right. Okay, so if I were to draw the influence line for dy, I'm going to scroll this up a bit so I can draw that kind of neatly. That's going to be the influence line for dy. Okay? Now, notice how I drew this beam, and I did this part kind of on purpose. Notice how the beam is 80 foot long, and the sort of dimensions are in 20-foot increments. So would it be a stretch to say that, you know, like this is 1/4, 1/2, 3/4, bless you, and 1.0? Is that okay? Okay. Now, the distributed load is from A to here, okay? So that's going to be from here to here. So, what is the area of that triangle? By the way, this, keep in mind, this dimension here, this horizontal dimension, 20 feet. So this is going to be 1/2 times 20 times 1/4. What is that? 2.5. So watch this. I propose that if we wanted to compute dy, what we're going to do is we're going to take, and I'm going to put a foot here just in case anybody's unit conscious here. So I'm going to say 1.3 kips per foot times 25 feet, okay? And I'm saying this is the area of that triangle, plus I'm going to say 25 kips times 1/2 plus 42 kips times 3/4. Now, how am I doing that? I'm saying the 25 is associated with the 1/2, the 42 is associated with the 3/4. And when you chug this out, what do you get?
Where did that 25? Shouldn't it be 2.5?
2.5. I'm sorry, 2.5. Thank you. You're like, what are you doing, Dr. Mike? 2.5. Thank you. So what do we get for dy? We get 47.25. So the idea is that by drawing, so the idea is that by drawing the influence line, I can directly perform the structural analysis. I don't have to write an equation of equilibrium. I just go bam times bam, bam times bam, bam times bam, sum it all up. Does that make sense? Is that kind of a mind-blowing kind of thing? I think it's kind of cool that you can use this tool to directly perform the structural analysis. Okay? All right. So, all right, any questions? Okay. All right, I'm going to start this next part of the lecture by throwing some terminology at you. Okay? So, what is the real application of influence lines? What was the main motivating factor? I mean, why did we even talk about influence lines to begin with? Why come up with this tool. Yeah, it's kind of nifty. It's like sort of a quirky way of solving reactions and whatnot. We just saw that. But the original application is moving loads. Okay? So let's go back to the question of moving loads. Okay? In fact, actually, I'll tell you what, to answer this question, maybe what I'll do is I'll actually go back to this example to sort of ask a question. Okay? What is the worst case vertical reaction at D due to a moving 50 kip load? What's the answer to that question? Let's think about that. Let me maybe parse this question out, maybe break it up into two separate questions. I have a 50 kip load. Here's my 50 kip load, and I'm moving it across the structure. If I want to generate the biggest reaction at D possible, where do I put the load? At D, right? Now, two reasons why. One, just common sense, but two, this is the largest value on the influence line, right? So the influence line tells you where to put the load to generate the worst case response. Now, with that, what is the worst case vertical reaction due to a 50 kip moving load? 50 kips. And how do you get that? 50 times 1. Does everybody see that? Everybody kind of thinking? Okay. All right. So, okay. So, if we want to get general, okay, let's look generally. Let's look at this part. Okay, so generally, an influence line, what we can do is, if we have moving loads, what we can do is, if they are concentrated loads, like my example here on the board, place that at the location of highest value. Okay. If it's a distributed load, place it wherever it's going to generate maximum response, right? So if I were to replace this with a moving 2 kip per foot distributed load, where do you put the 2 kip per foot distributed load? You put it everywhere, right? Because everywhere on the beam generates a reaction at D. And what is the reaction? 2 kips per foot times the area of the triangle, right? So for concentrated loads, place it at the location of highest value. For distributed loads, place it wherever you need to generate the worst case response. Okay? And so this results in what I call an envelope of results. So like the idea is we might have a dy max positive, and we might have a dy max negative, something like that. And you might go, what, this is a little confusing. I don't understand this. Bear with me. Okay, so let's consider this beam here. Okay, so I've got a simply supported beam, and I've drawn an influence line for the internal shear at section 1-1. So me just giving this to you, are you all okay with this? Okay, that makes sense? We have the jump, constant slope, negative 1/3, 2/3. Okay. Now, the influence line has negative area and it has positive area. We already talked about this a little bit in some of our examples, so hopefully I've set you up for this. So, going back to this, if I had a 2 kip per foot distributed load, where do I place it to generate the worst case scenario? And the way I worded that question is incorrect, because it really should be worst case scenarios. Okay? Here's what I mean. Okay, so here's the beam. Okay? I propose that to generate the worst case positive response, I would take this 2 kips per foot and put it here. Why? Because that's everywhere on the beam that has positive area, right? because, I mean, again, an influence line tells you what is the response due to a load anywhere on the structure, right? So there's nowhere else that I could place a distributed load and generate positive shear, okay? Now, how do I get that positive shear? I take 2 kips per foot times this area, and I get a value of 26.67 kips, okay? Likewise, for worst case negative response, I would say, okay, place the load everywhere else, okay? And how do I analyze the beam? Take 2 kips per foot times the area. And so I get what I'll call a worst case negative shear. And so what I'm saying is, if I have a 2 kip per foot distributed load, and I'm looking at this point on the beam, that point on the beam under this load sees a range of shears anywhere from this to this. And that's what we would design for, okay? Does that make sense? Everybody kind of okay with that? All right, does this make sense? Now, before I go to the next slide, let me ask one question. So I am assuming that this 2 kip per foot distributed load is transient, that it can go anywhere on the structure that I need it. What if the 2 kips per foot was everywhere and I wasn't allowed to move it? It was just a 2 kip per foot across the whole beam. I would determine the shear due to that load as 2 kips per foot times the sum of these areas, right? And this would be a positive area and this would be a negative area, okay? Does that idea kind of make sense? That if the load can't move, I would just take all the areas. If the load can move, I just take the worst case responses of either side. Sound good? Okay, the reason I mention that is because I want to throw some terminology at you, and I want to recognize that on structures, some loads are stationary, some aren't, okay? And I'm going to use the descriptions dead loads and live loads. The mnemonic that I kind of like to use is that dead loads are applied everywhere. And the reason I like to say that is because usually the most common dead load that we're going to consider is a self-weight of the beam. So like if you have a beam that weighs 100 pounds per foot, it's probably 100 pounds per foot everywhere along the structure, okay? So we would take 100 pounds per foot times all the areas. Now, it doesn't have to be just a distributed load. Like you could have a point load that's stationary, that's possible. But the main thing is that dead loads aren't going to generate an envelope. Dead loads are just going to give you an answer, okay? So dead loads, you're just going to put the loads on the beam, get the answer. And if it's a self-weight on the beam, it's probably something like it's going to be applied everywhere. Whereas live loads are going to be applied anywhere, okay? And the difference is that you move the live loads wherever you need to put them to generate worst case response. And so an example of live load would be traffic, like traffic on a bridge, okay? And so dead loads are going to generate like a single response, okay? Oh, sorry, I didn't mean to do that. Dead loads are going to generate a single response, so maybe like V sub D. I don't know why my pen's leaking like that. It's actually kind of leaking on the screen. That's kind of weird. But it's going to be like a V sub D, whereas this is going to be a V sub L plus V sub L minus. That's really weird why that's doing that. I'm just going to do that on another place. Okay, so I want to explain how influence lines work in regards to dead load and live load, and we're going to do that with this example. So one of the things worth mentioning about this example is that we've already drawn influence lines for it. This was our second influence line example, so we had already drawn the shear and moment influence lines for this section, and so we're just gonna kind of use them, but I'm gonna remind you of them and then sort of recopy them. So if I go back to like right here, those are these influence lines. Like we had already used these influence lines some time ago, okay? Everybody okay with this? I'm just gonna shamelessly steal them. So I'm stealing them from me. Copy. Okay, so we had drawn these influence lines before. I'll give you all a sec if you want to sort of jot them back down. But these are the influence lines that we had generated for this structure, okay? And just to make sure that we're sort of all aligned with what we're doing, okay? So what we're going to do is the following. We're going to have a dead load of 1.2 kips per foot. And then for live load, we're going to have a couple things we're going to have to consider. We're going to have to consider a 1.6 kip per foot. So maybe what I'll do is just make sure that this is moving. And then we're going to have a 25 kip load that's also moving. Okay? And so what I want to know is for this, I want to know what is the shear, what is the moment at this section, okay? And then for each of these, I want to know what is the positive shear, what is the negative shear, what is the positive shear, what is the negative shear. So in other words, what is the worst case response out of all of these? Okay? Does that make sense? Everybody okay with this? So, how am I going to deal with the dead load? Okay? So the dead load, let's do the dead load first. Actually, you know what? Let's not do that first. Let's do something a little different. Let's do some calculations on the side. All right, so bear with me. I'm gonna make some things a little easy. Okay, we'll go with this. Okay, so for this whole problem, what I'm going to need to do is I'm going to need to determine some areas under these triangles. Let's go ahead and do that now. So let's deal with shears first. So somebody help me out. What is the area of this whole triangle going to be? It's going to be 0.4 times 20 divided by 2. What is that? So 0.2 times 20, what is that? 4? Or maybe if you want, what you can do is you could say, you know, I mean, this whole thing is going to be 4.0. Is that fair? Okay. What about this triangle? So this is 0.7 times 14 over 2, so 0.7 times 7, so what is that? Negative 4.9? Is that fair? And then this one right here, what is that? Positive 0.9? Is that fair? Okay. All right, let's do this over here. So this negative one, 2.4 times 20 over 2. What is that? And I'm going to delete these. Getting those out of the way. Oh. There we go. All right, so what is this one right here? 24. And what about this one? 4.2 times 20 over 2, so 42? 42? Okay. Maybe what I'll do to make this a little easy, I did all that work. Let's get rid of these guidelines. I don't think they're helping. Okay. Okay. All right. So So let's conceptualize how we would deal with the dead load. So the dead load, where would we place the dead load? So the dead load sort of corresponds to how heavy the beam is. So we would place it everywhere, right? And so placing it everywhere, what we would do, so think about this as if it was a shear and moment diagram problem. We would place the dead load everywhere, we would compute reactions, we draw a shear diagram, draw a moment diagram, and then figure out what's the shear here, what's the moment here due to those loads, right? And that's how we would do the structural analysis. I propose an easier way of doing this problem is to just say that the dead load due to the shear equals what? The sum of those areas. And what is that? Zero. That's an interesting answer. It's almost like I'm tempting you to do this structural analysis problem, put the 1.2, get the reactions, and actually draw the shear diagram, and you'll find that it crosses zero right there. That's interesting, isn't it? You never would have seen that unless you drew the influence line. It's kind of crazy. All right, what about the moment? So what is that going to be?
$21.6.
21.6 foot kips, right? So, I propose that due to a 1.2 kip per foot dead load on this beam, there is zero shear right here, and there's 21.6 foot kips a moment right there. So in terms of dead load, that's what you would need to design for. Pretty easy, right? So what about live load? Okay, so let's deal with live load. All right. So, let's deal with the kip per foot first. How would we generate, so we're going to have a lot of calcs here, okay? How would we generate the worst case positive shear? How do we do that? We take 1.6 kips per foot times what? The worst case positive shear. Well, let me ask this way. This 1.6 kips per foot, it's a live load. It's moving. We can put it anywhere. Where do you put it to generate the worst case positive shear? Everywhere it's positive. So here and here and here and here, right? So that load, so if we were to draw a picture, it would be like that and like that. That's what would generate worst case positive shear. So what do I multiply the 1.6 by?
Or wait, 4 minus, or 4 plus 1.
Yeah. So all the positive area. So what is 1.6 times 4.9? 7.84. So what if that's the case, what's the worst case negative shear?
The same thing.
The same thing, because
It's also
okay. All right. So, how about moment? What's the worst case positive moment? times 42. And what is that? By the way, that unit's going to be square feet, in case you're curious about that.
67.2.
Say it again.
67.2.
And just so it's like crystal clear, every single one of these formulas represents what we would be doing is if we took the beam, put some loads on it, drew a shear diagram, drew a moment diagram, and then figured out what the value was there. And we're just doing it like this. So it's very fast, okay? Very fast amount of structural analysis. So what is ML negative going to be?
1.6 times -25.
Okay, and what is that? Negative 38.4. Okay. Does that sound good? Okay, let me do this. Bear with me. I'm gonna move this out of the way. Or no, you know what? I'm going to leave that right there because I think I've got room. I can write this right here. I didn't want to keep scrolling up and down. What about the 25 kips? How do I deal with the 25 kips? So, what is the worst case positive shear? What is the worst case negative shear? So it's going to be 25 kips times something, 25 kips times something. So help me out. Where would you place, so first off, how do we do point loads? Do we multiply by areas? You shook your head no. Why? You're right, Noel, if you did. You take 25 kips times what on the influence line? It's not the areas, just the values. So we would take 25 kips times what to get the worst case positive shear? So we're looking at this influence line. What's the highest? 0.4. That's the highest positive value for shear. So what this is saying is that if I take a load and I put it on the hinge, that generates the worst case positive shear right here. You never would have thought that would, I mean, without, well, I mean, I guess you could have probably reasoned it out, but an influence line makes it a boatload easier. So this is, was that 110? 100 and then a decimal point back, so that's 10. And then, so what are we going to do for the shear for the negative? What's the worst case negative shear? 25 times what? Negative 0.7. All right, and that's going to be, I think, like negative 17.5. Okay. What about moment? Let's do a moment. What do we get for the moment? So we're going to have 25 kips times something. So what's the worst case positive value? 4.2. Worst case negative value? Negative 2.4, right? That's feet for those of you that are unit conscious. Okay? And I think this is going to come out to 105 and negative 60. Okay. Has everybody been able to figure out and reason through what we've been doing so far? Does this kind of make sense? Okay. So, how do we summarize this? How do we package this into simple stuff. This is probably one of the first times we've ever had a problem where we had like 12 different answers. It's like, okay, what? There's so much different data. What do we do with it? Okay, so let's take a look at this. Okay, so let's talk about our worst case envelopes. Okay, so I've got like a V live load positive, V live load negative, and all this. How do I just figure out the range of shears and the range of moments? So just a V positive and a V negative. Okay. Well, one simple way of thinking about it is we could say, all right, let's just add up all the positives. So we'll say VL positive for the distributed load plus VL positive for the point load. And we could do that down here as well. But here's the thing about structures. Every beam must be strong enough to withstand its own self-weight. The dead load is there whether we like it or not. So we have to add the effects of the dead load to both of these because it's permanent. It's not moving, right? We have the flexibility to move the live load where we need to generate the worst case response. But we can't just ignore the dead load. It's there whether we like it or not. Does that make sense? So for both envelope reactions, we have to account for that. Okay? So what do we got? Now, I mean, the dead load shear was 0, so that didn't really matter. But let's do some bookkeeping here. So we've got, let's see, for the distributed load, we got, what was this? This was 7.84 plus, and then the point load was, what was the point load? Point load was what, 10 kips? This was negative 7.84 plus, and this was negative 17.5. Then I guess don't forget the 0. So this is going to be, what is that, 17.84 kips? And then minus what? Make sense? So my shear range on this beam is going to be this. And I'll make a comment here in a bit as to like, what does this mean from a design standpoint? And you all will discuss this when we take steel design next semester, or if you take reinforced concrete design next semester, we'll talk about this a little bit. So I'll make a couple concrete comments as well. Okay, so for moment, we're going to do the same thing. So we'll say ML positive for the distributed load plus ML positive for the point load. But again, we cannot ignore the presence of the dead load moment. It's there whether we like it or not. We have to consider it. Okay, so one of the things that you'll find with these problems is that more than anything, they are simply a bookkeeping issue. Okay, so let's see. For the distributed load, what do we have for, let's see, ML positive and ML negative was 67.2 and 38.4. So this is, okay. For the point loads, 105 and minus 60, was that right? But again, we can't ignore the dead load. Okay, so I might need your help on this. So what do we get for M positive and N negative?
M positive is 193.8.
Negative.
76.8.
Negative 76?
Negative 76.8.
Second? Okay. All right. So our range for our moments would be this. Okay. Okay, does anybody have any questions on the math that we've done so far? Okay, so let me say a couple of things about structural design. So this is going to be some comments for some of your later classes. And even though I'm teaching steel design next semester, I think the point is going to be made more succinctly if I talk about reinforced concrete design. So if you're planning on taking Dr. Zatar's reinforced concrete design, he'll sort of mention this. Well, I mean, it'll become a central theme of the class, but you'll see me mention it now. Makes sense. Okay, so if you have a beam, okay, and you bend it like this, it smiles at you, right? Okay, so we would call this positive bending, right? Okay. If it bends like that, it's negative bending, right? How many of you are in Dr. Na's 321 class right now? What can you tell me about the behavior of concrete?
Doesn't have to bend.
It's not that it doesn't like to bend. It doesn't like what? Doesn't like tension. Concrete is very strong in compression and it's very weak in tension. So if I were designing, let's say, a rectangular beam, right? If I was designing a rectangular beam for positive bending and I needed to put rebar in that beam, I would put rebar in the bottom of it, right? Because if I'm bending it, the top's experiencing compression, the bottom's experiencing tension if it's in positive bending, right? If it's in negative bending, honestly what I need to do is I need to put rebar up here, right? Because the top is experiencing tension if it's frowny face. Right? If I take the beam and I bend it in frowny face, the top is pulling apart, right? So what I'm saying for this range is we might have a beam that, I don't know, looks like that. Like it's got more positive range than it does negative range, so maybe more rebar on the bottom than you have on the top. You see what I mean? Maybe something like that. For the shear, if we were talking about concrete design, really all we care about is the magnitude. So we would actually be designing for the worst case negative shear than we would positive shear. Okay? And what we would do is the shear, so if we take this and extend it in 3 dimensions, the shear would tell us how far apart we space what are called our shear stirrups. So there's going to be these shear stirrups that go like that. And the closer that they are, the stronger the section is in shear. And so the higher this value, the shorter that spacing needs to be. And so the only thing worth mentioning, and then I'll let you go, is that we did this for this section right there. In practice, this exercise would be repeated 10th points along the span. And we're going to talk about that in more detail on Friday. That's all I got, everybody.